You want quick?
Oh,
Yes,
hello, hello. Yeah,
no. You can hear.
ah, hello. Good afternoon. I want to start the designing of the PID controller. So, for designing PID controller, first need to design either the PI or the P first, and the next one second. So, you can either design PI first and P, or the PD first and PI. Okay, there's a controller, compensator. So, and so it is more advisable to design the PD first before designing the PI, because for design the PI is meant to improve steady state error, and the PD is meant to improve the transient response. Assuming you design wait, let me go. Assuming you design the PI first, which is meant to control improve the steady state error. So assuming you have a system, maybe a system with transfer function of s equal to s plus a, s plus blah blah blah. You have improved the steady state error of this system. So that means you've reduced the steady state error to zero. And now coming to design the PD is meant to improve the transient response. By improving the transient response, it will affect steady state error. So what you've done using the PI will be cos 90. And in the book, they said another disadvantage is it will lead to over designing, but designing will also affect cost. So here it will be advisable to design the PD first before the PI. Let's click on. And we all know the transfer function for the PID compensator is the which can be like it's all the same thing. Sorry about that. Network. So for designing the PD controller, you just need to add a zero on the real axis. Just need to add a zero. But for the PI controller, add a pole at the origin and a zero, so a distance of 0.0 any distance are very close. Let's take this question. So over here we are told to given the system in figure 3.1, find a PID controller so that the system can operate with a peak time that is that of the uncomputed system at 20% with zero steady state error for a step unit for a step input. So the peak time is supposed to be test that of the uncomputed. That means the new T equal to 2/3 of the old T and the overshoot percentage overshoot 80. And we all know the formula for the peak time pi over omega d. And for the omega d, we know is omega n square root of 1 minus zeta squared. From the question, you can find your damping ratio as zeta using the overshoot formula. So you know zeta is equal to negative ln percentage overshoot divided by square root of pi squared plus ln squared percentage overshoot. So let's find our our damping ratio, zeta. Zero point. That's going to give 4, 5, 6. We know the zeta, and for zeta, it doesn't change irrespective of the peak time. The zeta is constant. That's the omega n, and it's the natural frequency. So you need to get your natural frequency of the old system. You need to find your new peak time for a new. That's what we use MATLAB to do. MATLAB. This was the system. We are coming to plot the. We are coming to plot the system in MATLAB. For the numerator. For here, you can either use this to key in the numerator 1 and 8. This is to just give we are just writing the coefficient of s. So the coefficient of s raised to the power 1 is 1. The coefficient of s raised to the power 0, 1 and 8. Over here too, you want to use this same method here. That means you need to expand right to be. So you can use the poly function where you input the roots of expression x, y, z. So coming back to the MATLAB, that's for the numerator. Now the denominator, you can those variables, they are just the num and then are variables. I'm putting the variables over there. But I prefer that. For the root of this expression is negative space -6 space -10. Terminate. Now you need to combine this. This is it's a transfer function. It's a transfer function. Maybe that transfer function. Go to the transfer function of the numerator over the denominator. Terminate. Now we got the, the zeta to be 0.456. So you doesn't let MATLAB know about your zeta. Let's go to 0.456. Now you're done with everything. Now it's left with you tell MATLAB how to plot it, like what to plot. So that's when you do the root locus of the gene. Now this is the root locus of the transfer function. Okay? And you need the graph to show the line with damping ratio 0.45. Now you come here and give the damping ratio S grade, 0. I should is it this the that transfer function. Now this is the point where transfer function touches the root locus of the transfer function touches 0.54 damping ratio line. Need to zoom to check out. Need to zoom to check out the properties over there. So over here, the gain is 0.12. The pull over here is negative 5.42 plus 10.6 D or I. The damping ratio here is 0.56. The overshoot is 20% in the question. Fancy much of it. Can write those points down. Oh, Charlie. Like, then I did talk we like I don't know say amuse.
All the time. 100.
Yeah, I don't know when I'll come to static.
I think maybe like maybe.
Say this second. I start.
For using it.
Now, now, now. Yeah, come to start again. I didn't know I was me. I can't start again. So the PI, we are coming to solve this question. Given the system in gas 9.31, design a PID controller so that the system can operate with a peak time. That is 2/3 of the uncompleted system at 20 zero steady state. Zero steady state error for a step in place. Solving this question. Let's write down the parameter. The T new, T peak new is equal to 2/3 of the T, and the overshoot, percentage overshoot, 20%. So you can use the percentage overshoot formula to find your negative length percentage overshoot over square root of pi squared plus then percentage overshoot squared, length squared. That's going to give you 0.456. 456. It has no unit. Now, and we know the formula for T peak is pi over omega d. And omega d is the same as is equal to omega n square root of 1 minus that squared. And you know your zeta. Zeta doesn't change. Zeta for the compensator system is the same as the zeta for the on the zeta for the uncompensated system. So, but it's the omega d that changes. So you need to find the omega d for the old system or the uncompensated. That's when MATLAB comes in. That's when MATLAB comes in. So we are going to plot. We're going to plot the system in a question on MATLAB. So this is the system. You're going to plot it on MATLAB. So first, for plotting it on MATLAB, you need to represent the numerator and the transfer function. If like equates this to a variable and plot it with so a variable, I'll give a variable for numerator equal to this. You can either use this or the poly. So for this, for using that, you can either represent for using that you can either represent this a square bracket and just write the coefficient of s. So the coefficient of x, s raised to the power 1 is 1, plus the coefficient of s raised to the power 0. We can either write the numerator as 1, or you can write it as the poly function. The poly function will just write it in the polynomial form, the roots of the equation. So for the numerator, I can either write negative, the root of that is negative, and that's all. I remember to close over here. The numerator, you're using this 1 and you terminate it. Then for the denominator, then equal to. Since it's in this form, if I want to represent it in this form, I now have to expand this. And expansion can make you go. I'll go with the poly side. Poly, then the roots are negative 3, negative 8, sorry, negative 6, negative 10. Terminated. Now, found your zeta to be 0.456. The any variable. I prefer z equal to 0.456. I need to plot the root locus. Hey, you need to give the transfer function to, you need to, I don't know, express the numerator and the denominator in a transfer function. So gen, a variable gen is equal to transfer function, numerator, comma denominator, terminated. Now you need to plot the root locus. You need to plot the root locus. R locus of gen of made a mistake, of gen, R locus of gen. So this is the root locus of this, the root locus of this. I need to now know where the root locus crosses the line with damping ratio 0.456. Need to know where the root locus crosses the line with 0.456. So now come and plot the line. S grade, the comma 0. Stop. Now the line shows. So this is where the root locus crosses the z gases. Hey, the root locus touches the line of damping ratio is now you have to know the point. So this is the point. This point has this properties. The gain is 1:1. The pool, the pool over here is this. The damping ratio, obviously, 0.456. But shooting question 2, frequency. So let's write down the properties. The gain was K. The gain was 1 to 1. Pole was negative 5.42 plus 10.6 I. The damping ratio and the rest. Don't really know. So remember in Opoku's class, today that the general formula for S is this plus minus that. So comparing this gives you your omega what? This is like to be equal to negative 5.42 and your omega d gets will be equal to 10.6. 10.6. So now you know your omega d. The omega d found here is your old omega d. So you can use that, place it in this formula, and find your new time, your new peak time, equal to 2 over 3 times pi over omega d. And omega d is 10.6. That way. 2 over 3 over 3 pi over 10, 0.198 and peak time. Time is seconds. 0.198. Now you know your new peak time. It's your new peak time. So your new peak time can help you find your new pool. Because for your new peak time, you can use it to find your omega n and your zeta, or your omega d, which will help you find your omega n. But sorry, zeta is the same. It's the same for the old uncompensated, the compensate. So the peak new will be equal to pi over omega d new. That is that your omega d new equal to your pi over your 0.198. That is 0.1. That will give you 10.7 omega d. Omega d is 15.7. So you know omega d. You want to find your, we know this equal to that omega n, because the axis you plot your the plot against the plot of this against omega d, and this is equal to that omega n, and this is equal to omega n square root of 1 minus that squared. And that line will be represented as that. Use your Pythagoras theorem, and Pythagoras theorem can help you find that the line is equal. So yes, now you know your new omega d. You need to find your new omega n, which is find your, so omega d all know is omega n square root of 1 minus that squared. That means omega n equal to omega d over square root of 1 minus that squared. Omega d 0.7 divided by square root of 0.45. That's going to give you 0 point squared, sorry, squared. squared. That will give you 17.83 natural 17.8. You know this. You know this. You know this. And we know this. So these three can help you find your new pool, the new position of the pool. The new position. The new the new pool will be, that is omega n plus my. Since the new pool is on the left hand plane, it will be negative automatically. Negative theta omega n omega d omega d. The zeta was 0.456 times the omega n was 17 plus minus omega d, or new omega d was 15. That will give us 4,570. So negative 0.13 plus because positive plus 10.7. So this is the new pool. Now, yeah, this is your pools and your zeros, and you are representing the new that's zero for the pool. Assuming this is the pool S, you need to find the position of, now that you've gotten the new pool. This new pool will help you find your position over here, the position where to place your new zero, because you need to find the angular contribution of all the poles and the zeros. Angular contribution of your zero minus angular contribution of your plus your poles plus that zero, the compensator zeros. Let's see. Be equal to an odd multiple of 180 plus 1 times 180. I'm taking k to 0. So it should be equal to 180. 180 over here. It is stress looking for your poles, the angular contribution of each and zero. You can use the calculator. So the transfer function, what is the transfer function? AS plus S plus 3S plus S plus 8 is equal to S plus 8. S plus 6, S plus 6, and S plus 10. So you need to find at this transfer function at the new pool. That will be at S is equal to negative 0.13 plus 10.87. You're going to get an expression. In that expression, you can use that expression to find your magnitude and your angle. And that angle found be the angle of the old pool, be the angle of your poles and zeros. Then you subtract that angle. That means your ZC 180 minus that angle. That angle you get So in the calculator, you need to convert your calculator to complex, complex, smooth and complex. Then input this transfer function, the x plus a, this transfer function on your calculator. X is not in the calculator or any in alphabet. S plus e over s plus 3 x plus 6, then x plus 10. Now after inputting it, you press solve. The solve is below the shift. Solve or the calc on the button with written calc. Press calc and input the value for x. That is this value. Negative 0.13 plus PSG plus 15.7 I IOG 28 and equal to, give you a complex number. You need to convert that complex number into its magnitude and angle form. So you press shift, then number 2, above number 2, the written complex. Shift, then complex, then 3. That will convert it to the magnitude and angular form. Then equal to, that's going to give the angle. We are not looking for the magnitude. So the angle there will be 161.6. That means your ZC 180 minus 161.3 comes 0.632. 180 minus 161.6. Change it back to your normal count, your normal mode. 180 minus 1. That will give you 18.3. That's your new angle for your zero. Now you know your new angle for your zero. You know your new angle for your zero. That means over here, this is the pole. Your new angle for your zero is 18.368. And you know the angle is measured from the positive axis. So if it's measured from the positive axis, that means your zero will be here. If this is your point, the line from your point, from the zero to your point. So this angle will be the 18.668. But you don't know the position of that zero. So Z2. And we know this point. This point is S equal to, what was it? S S is equal to this. S is equal to this. No. Negative 1 plus 20. S is equal to negative 8.13 plus 57G. So your real axis, this point. This point here is your real axis. That will be your negative 8.16. And this point here will be 10.7. Now, you know your angle, know your length, your opposite length, and your base length, your height and your base. Now, Pythagoras theorem. Now, those trig functions, tan is equal to tan theta is equal to adjacent. So pattern of your 18.36 equal to your opposite. The opposite here is the height. That's 15.87 divided by your length, your adjacent length here. So this length here will be, let's see, minus, okay, the length here. Let's see, minus 0.1 length here, length here, length here will be negative. Automatically you get your ZC to calculator ZC 17 by ZC equal to um, divided by some divided by 100. One we are getting we are getting this. This will be your the new position of your book. A minute coming. Hmm. Sorry, calculator error. I think it's 5.92. That'll be your position of your zero. We are done with the P. Now with your P, you know the general form of the PD as plus ADS. So since it's a pole, the transfer function of your p equal to x s plus 5.9. Because we know that s is equal to the position of the zero. S is equal to 55.92. That'll give you s negative 55.9. That'll give you s is equal to s plus 5 point equal to 0. That's it. So you're done with your PD compensation. You're done with your PD compensation. So this will be your form, your transfer function of your compensation. Now for the PI is very, just know that the PI is just a pole at the origin and the zero close to the pole. So a pole at the origin will be S and a zero close to the pole. So S plus a number close to zero. X plus, I'll take 0.1. So GI this. Know your transfer function of a PI and your P. And that's all. We are done with your PID compensation. So what you have to do is now you have your PI, your P here, cascaded to your PI, then your original system, gen. So you need to cascade. By cascading this to just multiply, or you cascade all the three. By cascading all the three, that'll give you a new your compensated system. That's is equal to S plus 5.92 S plus 0.1 divided by S. Cascaded these two. So for this will be your PID. For your PID, this PID. And you're coming to cascade your PID, your system, uncompensated system to get your head system. 5. S 5.92 and 0.2. S plus 5 and S S plus 0.1 divided by S. This cascaded with the normal, your original gene. That was let's see gene. Yes. S plus 8, S plus 3, S plus 6, S plus 8, S plus 3, S plus 6, S plus 10. So that means your transfer function of your compensated system will be S plus 55 point 10, S plus 0.1, 10, S plus 8, 10, S, S plus, S plus 6, S plus 10. But not forgetting there was a key over here. There was a key over here. Find that key, you have to now come and plot the transfer function, the compensated system, the transfer function of the compensator, and find where it crosses the line with damping ratio 0.456. Now we are going to edit that. Going to edit this. Copy this. Mm. Now you are coming to plot this transfer function. Yeah. We are coming to plot this compensate. Find your gain. Let's see. Plotting this. Now you assign your numerator to any value. Let's correct it. Plotting it common. Now mess it up. This can't use this. Need to use the poly, the root form. Poly. If you want to use this, you can go ahead, expand it. Poly, the first one is the root for the numerator is negative 5.92. So negative 0.1, negative equals terminate. So new denominator poly. Um, the root of this s equal to 0. 0 is s equal to s equal to negative 6. S equal to terminate. Now the rest is the same. Equal to 0.5. Equal to answer. R locus of m. Now the nth grade. Ah, stop. Now there's it. This is your new compensator system. That's your diagram for the see it touches points. I don't know why they picked like usually they pick the bar point. Like this is the point. Your gain is 5.18. Full is this, blah blah blah. So you gain 5.18. Come back to your so since your gain is 5.18, here becomes equal to 5.18 and the rest distance or distance come here. Want to vary to your transfer function of PID compensate PID. B A, then the S plus 5.9 5.92 S plus 0.1 divided by S. You expand this, to like something like this, something like this. You expand the transfer function to like something like this, something like plus A I over S plus, in case the question is like find the values of PI key, just expand, find the values of PI key. That's all. So PID, design a P. The PD is very stressful. Design a P, design your PI. So design your PD because like the T settling, the T settling 1/3 for your peak time, new peak time will go to 4/3/4. Uh, and use that, you plot your diagram on your MATLAB, find your pool where the which locus crosses the pool, the damping ratio line. Use that point, that pool, find your omega d or your omega n. Omega d will help you find omega n. Now find your omega n. Point to the find your TP. The TP value will help you find your omega n or omega d. Then after finding that, to help you find your new desired pool, new pool. After finding your new pool, now know the position of your new. Find an angular contribution of the rest of your present pool. Angular contribution, that one theta, that right. And your new pool, your new zero, angular contribution. That's after finding that, that will be equal to 180 minus the rest of your. After finding that, use your tan, your trig, and the theta ZC equal to that is your omega t divided by the length. That'll be your pi minus ZC. Find your ZC. After you find your ZC, the position, and your K, your PD controller will have one function of S plus the ZC. That'll be your PD. And your PI, we know, you all know is just the pole at the origin, S plus 2 close to 0.1 times over S. Sometimes they can your PDI will be, yeah, your P cascade, cascade, cascade the two of them by multiple. Cascade the two of them. Go and plot this your PID compensate. Cascade it, put one compensate. Cascade the PID on compensate. This is go and plot the compensate. Find where that crosses the damping ratio line. After finding that, that will help you find your D. And we are done. The question will find effective like it. Expand your PID compensator. That's your fine. Let's make it look like this. Then done. So So, so if you have any question concerning the PID compensation, ask it. Hopefully. So I think there's no question. I'll end it here. If you have any question, you can text me. We can text Rudy. Yeah, or Rudy or anyone. One can explain. Thank you so much for joining. Thank you.